Hi guys, welcome back to our new video on how to send parameters into the subroutines of 8085 microprocessor. So in the previous videos we have already seen how we can use a call instruction and make use of the subroutines. Obviously we have already seen this call instruction, and we also know when a call instruction is invoked or a call instruction is being executed. Let's say you have given a subroutine as sub, and let's say you have written the subroutine somewhere over here, and let's say you have instructions and return instruction. What happens first? The address of the next instruction that has to be executed will be which will be there in the program counter, will be pushed onto the top of the stack. PC will be pushed onto the top of the stack. That is the first process. Then the address of the subroutine will be pushed, it will be put into the program counter, and the microprocessor will start executing the instructions in the subroutine, right? So this is how a simple subroutine works. I think we have already discussed it in our previous videos. And when the microprocessor encounters the return instruction, what happens? The PC is popped back from the top of the stack and it returns back to the main program. And we have also seen that we use stacks for calling a subroutine, because we can have multiple subroutines or cascaded subroutines inside a program, which means that we can have another call instruction inside our subroutine and which can go into a new subroutine. So by using the stack, the advantage is that always the last in will be popped out first. So at this point again you will be pushing in the new address, the address of the next instruction in the subroutine, onto the top of the stack. And when we execute the return instruction, what happens? The last pushed address, which is the address of the PC, which is being pushed onto the top of the stack, will be popped out over here and will come back to the previous subroutine. So this is why we use stacks in case of pushing the PC. We don't have to push it, the processor does it, right? Whenever a call instruction is being executed, the processor does it. So like, as the engineers have chosen the stack because it will always follow the same return path, which means that it will come back to the previous subroutine and then it will go back to the main program. If you have one more subroutine, then it will come back in the same sequence. So I think we have already discussed all these things in the previous lectures. So I was just giving you an overview of what subroutines are and how the call instruction works. So here what we are going to discuss is that how we can send parameters. Parameters means variables or values into the stack. Let's say you want to multiply two numbers. So what do you do? Or let's say you want to add two numbers, or you want to do a 16-bit addition with using a 8085. So in order to do these additions or any of the arithmetic operations, or let's say you want to do any kind of functions, right, your instructions, you might have to send parameters into the subroutine, right? So parameters means values which has to be given. So in this case there are 4 different ways in which you can send data into the subroutine using different methods, right? So the first method we are going to discuss here is through registers. So you can directly put values into the registers, and you can take those values out within the subroutine. For example, let's say you put a value in one of the registers, let's say MVI D, 45H. So here MVI is the instruction move immediate, so which means that you are moving an immediate data 45 into the D register, right? And then let's say you are calling the subroutine, right? Let's say you have used, let's say you have used a subroutine name as add. You can give any label to the subroutine, it's up to you. So you have used a label add, and let's say inside the add subroutine you want to take this data, you can easily take it into the A register for doing any arithmetic operations. So move A comma D, what happens, the data that is there in D will come now into A register. So initially you put some data into the D register, and then in the subroutine you can access it and you can do whatever instructions you want to do within the subroutine, and then you can come back to the main program. The disadvantage here is that you have a very fixed number of registers, right? You have 7 registers. We know that there are 3 register pairs BC, DE and HL. These are the 6 registers, which are the 3 register pairs. So the problem here is that here you can only use a few of these registers, because definitely within the subroutine definitely you will have to use the A register if you want to do any of the arithmetic or logical operations. So definitely the A register must be free. So and HL registers are generally used as pointers, so you will again lose those 2 registers as well. So basically you have very few registers that can be used within the in this mode of transferring the parameters. So we can use D and the other registers, BC and all those registers, but still you might be short of registers if you have to send, let's say you have to send like 10 parameters or 12 parameters, then definitely you will be short of registers. Also even you can't actually fill up all the registers, because for you to work on or for you to do operations, you definitely need these registers. Registers are one of the most powerful tool that you have, so you can't compromise on your registers. But let's say if you want to just send 1 parameter, or let's say at the max 2 parameters, you can always use this mode of data transfer or transferring the parameters. So that's the first mode of transferring the parameters into the subroutine. Now let's look at the next method, or the next transferring method, that is through memory locations. So here what we can do is that you can choose a few memory locations and you can send data through these memory locations. For example, let's say I'm going to put MVI A comma 33H, and let's say I'm going to give an instruction STA 3500H, right? STA 3500H, which means that the data that is stored in A register will now be moved into the memory location 3500H, right? So 3500H memory location will get the data 33H, right? This is the store instruction, right? Now after that, let's say I'm giving a instruction. If I want to store multiple data, I can still do that. I can give again MVI A comma 45H, and then I can give the instruction STA 3501H, right? So I can do this, and then I can call a subroutine, right? Call a subroutine, and in the subroutine what I can do is that I can take out this data, right? I can take out this data using the instruction load instruction, right? LDA 3500H. What happens? The data comes into A register. If I want to move it into any other register, I can move it into any other register, right? I can give an instruction MOV any of the register comma A, and then I can again take the next data from LDA 3501H. Again the data comes into A register, the data that I've put. So first at this instruction, what happens, A gets the value 33H, and then I took that data into some other register. Then I took the data 3501, which means that A gets the value, this value, which is 45H, which has been stored at 3501. This was stored at 3500, right? So this is how you can take out the data using memory locations. Now here there is one more problem. Here, once you have written these addresses in the subroutine, see, the main reason why we write subroutines is that we want to execute these set of instructions multiple times at different parts of the code, right? So if you write these address locations, every time you access these subroutines, the data should always be there in 3500 and 3501, or the memory locations that you have given over here, right? So you need to make sure that the data is well set in this particular memory locations, and you are not allowed to use these memory locations for any other purpose, right? Because you'll be using it in the subroutine. So if you accidentally put some other data in this memory locations, and if you overwrite with the new data, what happens, you will lose the old data. So here you can this has a important use, because in many applications you can fix a certain particular memory locations for a particular subroutine, and then you can always use those memory locations for only those applications, or for only those subroutines. So I mean that is a flexibility that you have. I mean that is also a restriction, because these memory locations will always be locked for the subroutines, right? Another method that we have here is known as through memory pointers. Now we already know what are the memory pointers. The memory pointer, the HL register together holds the address from which you want to take the data, right? M is the register that has been used to indicate that you are taking the data from the memory, indicated by HL register, right? So first let's say you have to put some data into the HL register, right? For example, LXI H comma the address, right? For example, where you want to put the data, let's say 4500H, right? And then let's say you want to put the data into this memory location, you need to give the instruction MVI M comma 37H. So what happens, the data M stands for memory location. Which memory location? Memory location pointed by the HL register, right? So the data 37 now goes into which memory location? This goes into the memory location 4500, right? Now M is used as the to indicate that we are accessing a memory location pointed by the HL pair. Now here what we can do is that we can use this M, and then we can take data from any of the memory locations. For example, here let's say you give an instruction call subroutine. So in the subroutine you can give the instruction move A comma M. Now here the advantage is that the address is not fixed, right? The address is the address that is pointed by HL register, right? So HL can take any values. Here we have generalized it using a register M. In the previous case, if you see, we have given the address, right? Here we have given the address over here, and this address remains fixed. But in this case, whatever be the HL, whatever be the value that HL is pointing to, that becomes the address, which means that at multiple at multiple stages of your main program, you can change this value and give any address location where you want to store the data. But in this case, once you are done with one of the subroutine, in the previous case, once you are done with one of the subroutine, you have to delete that data that is there in. Basically, it's not deleting the data, you are overwriting the data at these memory locations, right? At 3500 or 3501, you will have to overwrite the data. But here you have a flexibility that you don't have to overwrite the data. You can use multiple memory locations. You can use any memory locations. You can keep changing the value of HL register pair, and then you can put any value into those memory locations using the MVI M comma any value that you want to put. And then in the subroutine, you are basically accessing the M register indicates that it's a memory location, and the memory location is pointed by the HL pair, right? So that is the advantage over here, that you don't have to fix to any of the memory locations. You are basically using a memory location, that's it, and you're using the pointers which are the HL pair, right? The HL pair will point to the memory location, whichever memory location at that particular point the HL pair is pointing to. From there the data will come into the A register, right? So this is a pretty more flexible method where you have a lot more flexibility on how to access the data, right? Now the last method is a bit complex method, that is through the stack, right? Now we have already seen how stack works and how we can use stack for subroutines, right? So here the how we can use stack is that, let's say you want to put some data, into you want to transfer data through stack. So we have already seen how the stack works, right? So first, let's say this is your memory locations. You have memory locations, right? A lot of memory locations you have. Now what we can do is that we can put some data into any of the registers. For example, LXI D comma 4352H, right? This is the data that you want to transfer through the stack, right? Now what you have to do, first you will have to put this data into the stack. So what you will what is the instruction? The instruction is push D, right? So when you do push D, what happens? The data that is there in the D register that will get pushed onto the top of the stack. For in this case, what happens? The 43 goes into the stack, the D goes here, and 52 goes over here, right? SP is pointing to the top of the stack, right? Now what else? What can you do now? Let's say you are calling the subroutine, right? Now when you call the subroutine, what happens? When you give the call sub instruction, the return address, which means that the address of the next instruction, the PC holds the next address of the next instruction, that is going to be pushed onto the top of the stack, right? You're going to put it onto the top of the stack. So the return address is on the top of the stack right now. SP is pointing to the top of the stack, right? Now this is how the stack grows, right? Now here you have the subroutine, right? This is your subroutine. Now if you pop your date, what will come first? The data is not going to come first, but the return address is going to come first, because on the top of the stack you have the return address, right? On the top of the stack you have the return address. Therefore when you pop, it is not the SP that is going to it is not the data that you have over here that is not going to come out, but it is the return address that is going to come out. So but if you want to take out the data, there is no other way. You will have to give the pop instruction, right? So you will give the instruction pop. here we are going to use register H. Now there is a reason why we are going to use this register H. The reason we'll be discussing as we move on further, right? So we'll pop the return address into the HL pair, right? H means it's the HL pair. So the data is being popped into the HL pair. Now you have, it's not the data, it is the return address. The return address is popped onto the HL pair. Now we'll take out the next data that is there in the bottom, right? Now after popping out this data, what happens? The SP is now pointing back at this particular memory location. It has come back to this particular memory location, right? Now again you will give a pop instruction, pop B or any of the pair register pairs, so that what you will get, you will get the data in BC register, right? 52 and 43 will go into the B register and 52 will go into the C register, right? This is how it pops out. So the data that is there in the data 43 comes into B, 52 comes into C. Now what you can do, now you can do whatever operations you want to do, right? Now right now the SP is pointing to this particular memory location, right? So what happens if we write a return instruction? Now at this point, if we write a return instruction, what happens? SP is the program counter. The program counter will get the data from the next two memory locations, right? From here and here, the program counter will get the data, and this could be a garbage value, right? Because the return address was over here, and right now if you give a RET instruction, what happens? The data that you are popping out will be some other data, right? It could be some garbage value, and it is not going to go into this particular memory location, right? This particular memory location. So this can't be used, right? We won't be able to use this particular instruction over here. Return instruction will end up giving the program counter a garbage value, right? So but you have already taken out the return address in HL register, right? We have already taken out the return address in HL register. What we can do is that we have an instruction that is PCHL, right? PCHL. What happens? The data that is there in HL goes into PC. We have already discussed this instruction. So the data that is there in HL pair goes into PC, and automatically it comes back to the next instruction that has to be executed in the main program. Is that clear, guys? So this is a very important instruction, PCHL, because we have already studied this instruction. This is the reason why they have designed this particular instruction, PCHL, so that if you want to send data through the stack, you can always send the data. You can take out the return address into the HL pair, you can take out this return address into the HL pair, and then do your functions. You can pop out n number of data, how many number of data that you have pushed into the top into the stack. All these data you can pop in over here, and then finally instead of return instruction, you will have to use the PCHL instruction, where PC gets the value from HL. What does HL have? HL has the return address, right? HL has the return address, and the return address will be put into the PC. Automatically the program counter goes into the main program and start executing from the next instruction in the main program. Is this clear, guys? This is one of the wonderful ways in which you can use the stack for transferring parameters. Now stack has few other uses also. For example, if you want to put some data into the flag register, PSW, right? Now if you want to put some data into the flag register, the only way you can do is by using the stack register. I mean using the stack. For example, let's say you want to put some data into the PSW 45, right? 45H. This is the data that you want to put into the PSW register. What you can do is that you don't have any access to the PSW register apart from using the stack. So this is the only way you can access the PSW register. The way is that you can first move it into MVI C, 45H, right? What happens? The data that is there in the data 45 goes into the C register. After that you can give a push B instruction. Now what happens, the register pair B goes into the top of the stack, right? What happens, the B is over here, the C is over here, C which is 45 is over here, right? C is the register, 45 is the data that is there in the register that goes into the top of the stack. Basically C doesn't go, only the data goes, right? Now once you have pushed these two datas, you can give an instruction pop PSW. Now one thing you have to remember is that when you give pop PSW, the B that you have stored goes into the A register and the C that you have stored goes into the PSW register. That's why we have put the data into C, not into B, right? So you can first put the data into C, push BC. This is the BC pair, so push, because push and pop instructions always happen as a 16-bit operation in 8085 microprocessor. So whenever you give a push instruction, push B, basically two registers gets pushed onto the top of stack, which is one is B and the other one is C. And when you pop out PSW, it will pop out A as well as PSW. So PSW, C will get the PSW and A will get, sorry, PSW will get the data that is there at the top and A will get the next data that is there, right? SP will be pointing out at over here, it will come back to here, and then you will get the data in A. So this is how you can push data into, or you can alter the data that is there in the flag register. You can't directly put data into PSW, no, that is not possible. The only way in which you can put data into PSW is by pushing and popping the data. Similarly, if you want to read the data from PSW, again you can use the stack. You can give the instruction push PSW. What happens, the data that is there, A and PSW together will be pushed onto the top of the stack, and then you can pop to any register pair, for example B. So what happens, the data that is there in A comes into B and the data that is there in C comes to the PSW register, and then you can analyze the data that is there in PSW register. I hope the video is clear, the concepts are clear. If you have any doubt, you can contact me. Okay then guys, thank you.